All right, here we go. This is problem number 13 from chapter 9 of the Holiday and Resnick textbook. So we've got this shell that's being fired, and the problem tells us that it's being fired with an initial velocity of 20 meters a second at an angle of 60 degrees above the horizontal. Okay, and so the idea is it's going to have a horizontal component of, if you do the trig, 20 times the cosine of 60, so you get 10 meters a second, and an initial vertical component of 17.32 meters a second. Okay. So what happens is the shell goes up into the air and it explodes. Okay. So up until that point, let's figure out how far it's traveled to there. So in order to do that, we got to find the time it took to get to the peak of its path. So let's, all right. So to get to the top, here's what we know. T peak. Well, here's an equation. I know that time is Vfy minus Viy all over my acceleration vertically, right? So at the peak, my Vfy is 0, my Viy is 17.32 meters a second, my acceleration vertically is negative 9.8 meters a second squared. So the time to get to the top of the path turns out to be 1.77 seconds. So this displacement here is just going to be how fast I'm moving horizontally, 10 meters a second, times 1.77 seconds. So my displacement there is going to be dx times t. So 10 meters a second for 1.77 seconds gives you 17.7 meters. Okay? Now, the next thing we need to do is we need to deal with this second chunk. All right? So what it tells us is that the shell splits in half, okay? And one chunk of the shell just falls straight down, and the other chunk of the shell is, going to get pushed forward. Okay? So in class, at least this year that I'm recording this, I did this problem, and I did kind of a hand-wavy explanation, all right? And what I said was this. So the idea is, at the top of the path, everything is moving horizontally at 10 meters a second. The explosion causes half of the mass to lose 10 meters a second. And so conservation of momentum tells us because the masses are equal, the other chunk has to gain the same amount of velocity. So it can gain another 10 meters a second. So that means the chunk that gets fired forward is now moving horizontally at 10 meters a second plus another 10 meters a second for a total of 20 meters a second. Okay? But that's a little bit hand-wavy, so I feel like maybe I should give a better explanation of it. All right? So here's maybe another way of thinking about it. So I know that the velocity of the center of mass at this point is 10 meters a second, and that's got to stay constant, right? So here is what we can do. I know that the velocity of the center of mass should equal to, we've got two chunks, right? So there's the mass of chunk 1 times the velocity of chunk 1 plus the mass of chunk 2 times the velocity of chunk 2 all over the total mass, which is mass of 1 plus mass of 2. So let's plug in our numbers. So I know that the velocity of the center mass at the top has got to be 10 meters a second. Now, I know my two masses are equal, right? So instead of distinguishing between M1 and M2, I'm just going to call them M. So here, this first chunk has got a mass of M, but remember, its velocity became 0 after the explosion. And then the second mass has the same mass, and we're trying to find its velocity. All over, mass 1 and mass 2 are the same, so 2m, right? So what I end up with is this goes away. So now I've got m times v2 over 2m. These cancel. So I get 10 meters a second equals v2 over 2. Oh, that means that v2 must be 20 meters a second. So that means that it's going to go, since it's going twice as fast, it's going to go twice as far. So the second displacement is going to be 17.7 times 2, which is what, 35.4 meters. So then just add up your two distances, and that gives you 53 meters. Okay?